Hello everyone, this is lecture 3 of NPTEL course on remote sensing for natural hazard studies. This is part 2. So, we will continue our discussion on the geometric errors. So, geometric distortion in remote sensing images that we have already discussed, and now we were discussing about what is the impact or what is the benefits of the geometric correction. As we discussed, geometric correction will help you to remove the geometric distortion as well as it will place the individual pixel at their proper map location, right? And it also allows us to estimate the accurate distance, area and direction information. Now we will try to see how actually this distance, area and direction information is estimated. So let's say this is the satellite image, right, produced by this particular sensor. Now these images are basically nothing but the pixels arranged in an array, right. So these pixels are generated by individual detector which are here, right, and we call it IFOV. This is IFOV. And let us say within this field of view you have this kind of topography. So what will happen to this particular pixel? This will have less area or maybe larger area depending upon the topography covered within this. But we generally say this satellite image is having 30 by 30 meter or 1 by 1 meter or 0.5 by 0.5 meter, right. So in such situation what will happen? The role of this topography is very critical, right, or the curvature of the earth. So what we do in this particular geometric correction, we try to provide the accurate shape and size information to our pixel and also their location. So if we say that this is 30 by 30 meter, right. So this is actually representing the 30 by 30 meter and the features captured in this particular pixel is actually matching with the feature present on the ground. So this overlapping, or if you overlay these images together, so they will match with each other. So that is very important. And once you have the appropriate size of the pixel, that means you can say that 4 pixel covering the water body. So the 4 pixel means 4 into 30 by 30 meter, that is the area covered by the water body, right. So the area estimation is very easy when you have the proper map location and the size of the pixel. Now another thing, from here to here if you want to go, whether this path you have to take or you have to take this path or you have to take this path, the direction information is also very important here. So this is the concept which is used in the Google map when you try to search that how much time it will take to reach this particular location, then it will find the available routes and then it will show how much time it is taking to reach at a particular velocity, right. So in such situation this geometric correction is very important. Geometrically corrected images can be used directly as an input in geographic information system and spatial decision support system, because we are supposed to remove the geometric errors and then the images will be free from the geometric error and that can directly go as an input in our GIS or SDSS platform. Better cartographic accuracy, useful to analyze temporal images of different sensor of different resolution. Let us say 1 pixel is 30 by 30 meter, right. Another pixel is 0.5 by 0.5 meter. So when we are having the proper map location and the shape of the pixel, what will happen? This will go and it will sit over its own position, right. So it will not occupy this 30 by 30 meter, it will just go and sit on its own location. So the next pixel will be here like this, it will make 0.5 meter, that will fit into this 30 by 30 meter, right. So depending upon the size, the number of pixel will be accommodated within the 30 by 30 meter. Geometric error in satellite images are grouped into internal and external errors. Internal and external errors can be introduced by systematic, which is predictable, because if something is systematic, we already know about them and we can model them, and non-systematic, that is random sources. So the random sources, it is very hard to identify and hard to remove. The systematic errors are comparatively easier to identify and correct than non-systematic, because non-systematics are the random one. Here you can see this particular sensor is looking at this particular ground, right, and before correction your image will look like this. Here you can see this is the before correction image. So you will get a strip, and then in this you will have all these pixels, right, and associated values. But remember, Earth is rotating and your sensor is moving from one place to another place, isn't it? So your sensor is moving in an orbit and your Earth is moving in this direction, right. So what will happen? After correction you will find that due to the movement of Earth and the satellite in their orbit, this kind of error was expected, right, which is not present in the raw data, that you have to correct. It is because of the Earth's rotation, right. So then what we do is we try to generate the corrected image, and these columns will have null values, right. Similarly here all these will have null values. So this is nadir IFOV, this is off nadir IFOV, and here you can see the size of the ground captured by this particular detector at the nadir, it is smaller than the off nadir IFOV, right. So this kind of problem you will have before the geometric correction. Once you apply the geometric correction, all the pixels are in the same spatial resolution. This slide explains what happens because of the Earth rotation and the rotation of the sensor. So this was supposed to be like this. So this is the area which is supposed to be captured, but because of the Earth rotation, you see the road is coming like this, which is having some curvature. So this kind of error is getting removed because of the geometric correction, right. So the variation in ground resolution that we have already seen, at nadir it will be smaller and off nadir it will be more elliptical, and because of that your coverage will be more here than this one, right. Here you can exactly find a best fit square. So the pixel at nadir will have no geometric distortion. As we go away from nadir, off nadir, pixel size will be changed depending upon the flight altitude and IFOV. The relief displacement, objects at the nadir will have only their tops visible, while top and side of off nadir object, because when you see from this side will be visible. Here it will be only the top view will be visible for this object, right. If the objects are tall or are far away from the center of the image, the distortion and the positional error will be larger. This result in the compression of the image feature at points away from the nadir. This is called tangential scale distortion, right. So here you can see this is one very good example. When you are having the nadir looking pixel, only the top will be visible, right, and you can easily find what are the pixels with the off nadir. So here you can see the off nadir. So here the sides of the objects will be visible, right? So now we will talk about the external geometric error. It is introduced by the random movement of the aircraft or spacecraft, which may vary in nature through space and time. So here you can see this spacecraft or aircraft, it can change its direction in these angles, right? So here one, this is another one, this is. So this is very important to understand. Changes in altitude, changes in attitude is affecting our remote sensing data. This kind of error is more in the airborne survey, because there the flights are manually used, whereas in the spacecraft the orbit is fixed, so there is a very less chances of getting any changes in the altitude or attitude, right? So the altitude changes, if you are changing the altitude, what happens? So if you consider this satellite here, which is looking at this particular ground, and here you are having 1 pixel, let us say this is 1 pixel, this is at 100 meter from sea level, right? What if this level is, because of the topography, it is 200 meter from MSL, because IFOV is fixed, this is IFOV, altitude is fixed because we are talking about the spacecraft measurement. So this is, let us say 3000 kilometer. So when we are having the IFOV and altitude fixed, we can estimate how much area it will cover, but actually because of the variation in the topography, this was not constant, this 3000. So in such situation you will have the problem with the object captured within the field of view of one detector, right? So this is called ground swath width at nadir, and off nadir what will happen? The field of view is theta here and IFOV is beta here, right? So this is very clear from this diagram. The spatial resolution of remotely sensed image is a function of the IFOV and altitude, right? Now we will talk about the attitude changes. So airborne platforms are significantly influenced by atmospheric turbulence and wind. Because of the turbulence and the wind, what happens? There will be change in the altitude of the sensor, and that will lead to the change in the pixel size. Due to different wind direction, remote sensing platform may rotate randomly in 3 different axes, which is roll, pitch and yaw, which is represented here. Airborne remote sensing system have gyro stabilization unit that minimizes or remove the effects of pitch, roll and yaw, right? So in addition, remote sensing images with such distortion can be corrected using ground control point. So now this ground control point is very important. So we also call it GCP. So a GCP is a location on the surface of the earth with known latitude and longitude that can be identified easily and accurately on the remote sensing image and map. Because what happens, you have, let's say, a satellite image which has pixels, and these pixels are having latitude, longitude and DN values. Right. Now with DN value you can put those latitude longitudes in your mobile phone or in your GPS, and then it can show you where you have to go and find that particular point. So that will be the center of this particular pixel, right? So this is called ground control point. So when we are having one location which is from the ground, right, let's say this is a temple or mosque. So this location we can note through our mobile phone or through our GPS, and then we try to locate in this particular image where it is, right. So that is called ground control point. So here this is one example, this is the satellite image, this is a topo sheet. Now in this satellite image, this is the boundary of this particular object. Here this is the boundary of this particular object. So, this particular corner and this particular corner both are same. So, we can easily identify them. This is not done visually. When you put the values, automatically your remote sensing software will tell you where it is exactly in your remote sensing image. So, selecting the location of GCP is very critical, because with time the GCP should not change, because if you are collecting a GCP, let's say today, and you are trying to use it after 10 years, then you have to make sure that those GCPs that you are going to use after 10 years, they are constant through time, they are not changing. So, choose features that are stationary and unlikely to move, high contrast feature with the surrounding, because then it will be easy to locate in your image. Features should not be very big or very small, so that their exact location can be easily pinpointed in a single pixel, right. So, you have to take care of that. Features not recommended as GCP. First one is river bank or course, because with time they are changing. The lake boundary also get changed, forest boundary also get changed, political boundaries may change, agricultural landmarks are changing very frequently, because if one person sells, the next person may merge with some other plots and then the boundary will change. Then what are the different sources of GCPs? The first one is the topographic map, that toposheet, which is generated by the Survey of India. So, that can be used as your reference map, or georeferenced digital image, that one image that you have already georeferenced, and then that can be used later as an reference for correcting a new data. Then global positioning system, the GPS, the mobile phone information or the latitude longitude measured with your mobile phone, those are not accurate. So, in remote sensing, when we are trying to do qualitative or quantitative analysis, we generally prefer this GPS, right. Now, we will talk about the types of geometric correction. The first one is the map rectification. Another one is image to image registration. So, as I mentioned, that toposheet, basically they are generated by the Survey of India in India, right, and toposheets have some latitude longitude marked over this soft copy or hard copy maps, right. So, these maps will be used, or these latitude longitudes will be used to correct the geometric error of this particular toposheet. Once we are having this rectified map, then we can use this as image to image. So, here this image will be your referenced image, right. So, first we will go with the map rectification if you have only one toposheet. And if you are trying to correct your satellite image, then first you need to have a reference map. It can be directly from your GPS or it can be from a toposheet. So, used to estimate the accurate area, direction and distance information. It requires GCP or registered map coordinate corresponding to the unregistered map coordinate. That means your image that is captured by a satellite, it is basically unregistered. And then you have the GCP from the field, or maybe registered map from one of the example is toposheet, that you will be using to correct this unregistered image coordinates. The reference and target image of the same topographic area and aerial extent are needed. So, the spatial extent of toposheet and the satellite image both should be same. Through translation and rotation alignment process, target image will be adjusted for each pixel with respect to a reference image or provided ground control points. Geometric registration of image. The process of projecting two or more images of an area acquired by different sensor into a single coordinate system based on the transformation parameter and the production of the best match at the pixel level, right. So, here we have two parts of the geometric rectification. So, first one is spatial interpolation and the next one is intensity interpolation. So, the spatial interpolation, basically we are trying to reorient our pixel, right. So, the same feature in both reference and target image must be identified. So, now you are having a topo sheet which is corrected and all these points are known, right, and then this is your unregistered map which is basically your satellite image. So, here same feature in both reference and target should be used. So, let us say here you have a building which is not going to move and here this is the building, right. So, I am selecting this particular pixel here and this particular location in the map. The coordinates of the target image pixel referred to as x dash y dash and the corresponding pixel coordinate in the reference image is xy. So, this is xy and this is x dash y dash. Using such information, a relationship between reference and the target image is established which is used for the geometric coordinate transformation. Now, suppose this is first ground control point that we are taking from the topo sheet. Another one is, let us say this is one feature, this is another feature, right. So, second point we have taken. So, this will be x1 y1, this will be x dash y dash and then this is the second point. So, similarly you will have to identify good number of points so that you can generate a correlation between these two. Polynomial equation based on least square criteria are used to establish the relationship between the reference and target image coordinates. Depending upon the degree of distortion in target image, number of GCPs and order of polynomial equations are decided. So, here you can see here this is the first order, the blue one, the second one is here, this is the third order, yellow is the fourth order and this one is the fifth order. So, fifth order is representing this data variation very nicely, right. So, depending upon the degree of distortion in the target image and the number of GCP, order of polynomials are decided. Geometric coordinate transformation addresses the following types of distortion in remote sensing images. First one is translation in XY, then scale changes in XY, then skewness and then rotation. These all will be addressed in the geometric correction. The number of GCP required for different orders of the polynomial equation can be estimated through this equation, which is n is equal to p plus 1 multiplied with p plus 2 multiplied with 0.5. So, p is the order of polynomial and n is the number of GCP required. This is very important that you need to select appropriate number of GCPs depending upon the polynomial equation that you are going to use for spatial interpolation. To evaluate the accuracy of the spatial interpolation, root mean square error RMSE is used, right. So, this is the general formula of RMSE, but here one thing which is very important, that if your RMSE is coming 0.5 or if your RMSE is coming 1.5, right. So, what will be the difference? So, that it says that if your processing is having RMSE of 0.5, that means object which was supposed to be within this particular pixel might be diverted from this particular original position with 0.5, that means half of the pixel, right. So, it is within this particular pixel, right. But when we say 1.5, that means it is going beyond this boundary and it is getting located in the next pixel. So, it is a thumb rule that this RMSE should not be more than 1 pixel, right. So, this is very, very important. Why? If it is more than 1 pixel or if it is more than 1, what will happen? The feature is getting shifted to another pixel, right. Now, we will talk about the intensity interpolation. So, this process involves the extraction of brightness value from the target image, right. So, what is happening now? From the spatial interpolation, what we did? We have reoriented the pixels so that their shape and size are consistent, right. Now, this is the raw data, let us say, and here you have the pixel values. So, which pixel value will be located here? Whether it will go here or whether it will go here, whether it will go here after the spatial interpolation. So, for that we have to do this intensity interpolation. So, here basically we are talking about the DN number, how they will be placed in a particular pixel. So, pixel value from the target image can be extracted using the following resampling technique. The first one is the nearest neighbor, next one is bilinear and the third one is the cubic convolution. So, the nearest neighbor resampling technique, it says that it will be using the closest pixel value, right. So, it will be using the closest pixel. So, this is the target, this is the rectified image, right. Now, when we talk about the bilinear, what we will do? We will be using the average of 4 adjacent pixel and that value will be placed here, right. In cubic convolution, what happens? We are using 4 by 4 pixels to calculate the average and then it will be placed in the target or in the final output, right. So, the difference between the cubic, bilinear and the nearest neighbor is the resampling and the averaging of the pixel value. So, now suppose your objective of the remote sensing is to identify the material characteristic, right, or material whether it is present or not based on the characteristic absorption feature. Now, if you have used the bilinear or you have used the cubic convolution, what will happen? You are using the averaged one, you are using the averaged value. So, the real value which was captured by the sensor, it is getting changed and this averaging is having the equal weightage from all these pixels, right. So, if it is averaged, real value is lost and that value cannot be used for any quantitative analysis. You cannot use any image which is corrected through cubic convolution for material identification using the characteristic absorption feature, right. So, that you have to be very, very careful. Now, this is the example of your geometric correction. So, this was the input image and this is the output image. Now, we will talk about the radiometric error. So, the response of remote sensing sensor cannot be linear, right. So, one thing that we discussed, that this is the sensitivity of a detector, right. So, it says that 400 to 500 nanometer wavelength energy it can absorb or it can sense, right. But if you see, this particular region is not having a good sensitivity, right. So, it cannot be linear. The sensor launched for remote sensing essentially go through pre-launch and in-orbit calibration. In a remote sensing image, noise error can be introduced at several stages. Radiometric is one of the noises introduced by the sensor system to the remotely sensed image. It results when an individual or set of detector do not function properly or improperly calibrated. So, the radiometric error are generally introduced in the remote sensing system by mechanical, electrical or communication failure. sometimes the detector stopped working, sometimes it will be for a moment, sometimes it will be for a longer period, sometimes during the data transfer to the ground station, that in between there is a loss of signal, because of that there may be change in the value or missing values will be there in your image. These are the unwanted disturbances or noise in the final image due to flaws in the remote sensing instrument, electronic disturbances between sensor component and potential distortion in the data recording processes. So, there are different types of radiometric error. The first one is random bad pixel, then line start or stop problem, line or column dropouts, partial line or column dropouts, line or column stripping, smile and artifacts, adjacency effects. These are the errors because of the radiometry. Now, this is one of the example of line or column dropout. Here you can see this particular line which is here, it is a error, right. So, this is one of the detector stopped working, right. So, that we have removed from this particular image, you can't find anything here, right. So, this kind of radiometric correction takes place in a remotely sensed image. This is another example. Here you have N line stripping. So, you can see these white lines, right here, and these are the radiometric error. This is called N line stripping. So, after correction this can be removed, right. So, that is all about the errors in the remote sensing data. With this we are finishing this lecture. Thank you.